Hello everyone, in this video I'm going to show to you how to derive the probability density function or PDF for t-distribution. The random variable for this t-distribution has this formula: the sample mean minus the population mean over the sample standard deviation over square root of n, where the sample mean in here has this formula, the sample standard deviation in here has a formula square root of this. This x sub I in here and in here are the sample random variables. They are n of them, so this n in here is the sample size or the number of samples. These random variables in here must be IID, so they should be independent to each other and they should have identical distribution, which is a normal distribution, so they should have the same population mean mu and have the same population variance sigma squared. Now to derive the PDF for t-distribution, we need to do 3 steps. The first one is to re-express this expression in here as a product of a random variable which has a known distribution and a function of another random variable v also with known distribution. This u and v in here must be independent to each other. Then after this, for step 2, we can then determine the joint or the mixed PDF for this u and v in here. So we have here the joint or mixed PDF for u and v. Since this u and v are independent to each other, then it is equal to the product of their individual PDFs. So we have here PDF for u and PDF for v. Now since this u and v have known distributions, then we can determine their individual PDFs. And then from here, can transform it into another joint or mixed PDF, but this time in terms of our t random variable. So we have here t and then a dummy random variable w. We can do this transformation using this relationship in here and another one for this w, which is just equal to one of the random variable v. And then for the third step, we can finally derive the PDF for t-distribution as the integral of this joint PDF in here. With w. So now let us proceed with the step 1. So in here, let us copy this expression in here. So we have here then from here we can multiply both numerator and denominator by the population standard deviation sigma. Then we can replace this s in here by sigma, so we have here sigma over square root of n, then times sigma over s. And then for this expression in here, we can designate it as u. And some of you already know that this expression in here has a standard normal distribution. Now for others who want a proof for this, that this expression in here has this distribution, I will provide the proof at the end of this video after deriving this PDF for t-distribution. So we have an appendix for this video which is proving that this expression has this distribution, which is a standard normal distribution. Now please take note that the proof for this is not the central limit theorem, because this n in here does not need to approach infinity, and the x bar in here is the sample mean for the samples with normal distribution, not any distribution. So this is not central limit theorem. And then for the sigma over s, we can express it as 1 over its reciprocal, which is s over sigma. And then we can square this whole term. So we have here s squared over sigma squared, and then we need to raise the whole term by 1/2 to not to change its value from here. And then from here, we can multiply both numerator and denominator by n minus 1. So we have here n minus 1 over n minus 1 times s squared over sigma squared. And then raised to 1/2. Now for this one, we can designate it as random variable v, and this v, which is this, has a chi-squared distribution with n minus 1 degrees of freedom. Now if you want to prove for this one that this expression in here has this distribution, I have a video for this one and I provided the link in the description below so that you can check it out. We can then express this t in here to be equal to this u, and then times this. So we have here n minus 1 over v, and then raised to 1/2. Now for this random variable u in here, this n, mu, and sigma are constants, so this u is a function of x bar only, or the sample mean. And then for this v, since this sigma and n are constants, then it is a function of this s squared, or the sample variance only. Now this sample mean and sample variance are independent. Now if you want to prove for this one that the sample mean and the sample variance are independent to each other, then you can find one of my videos showing how to prove this, and I provided the link in the description below so that you can check it out. Now from here, since this sample mean and the sample variance are independent to each other, then their functions should also be independent to each other. So this u and v, so we can put it then u and v are independent. Now from here, we are done already with the step 1, which is this. And then for the step 2, we can have a joint PDF for u and v. And since they are independent to each other, then it is equal to the product of their individual PDFs. So we have here PDF in terms of u and PDF in terms of v. Now for this u, it has a standard normal distribution. So we have here PDF for a standard normal distribution, which is 1 over square root of 2 pi times e raised to negative u squared over 2. And then for this v, which has a chi-squared distribution with n minus 1 degrees of freedom, it is equal to 1 over gamma of its degrees of freedom, which is n minus 1, and then over 2, and then 2 raised to its degrees of freedom, which is n minus 1, and then over 2. And then we have here v raised to its degrees of freedom, n minus 1, and then over 2, and then minus 1. And then we have here e raised to negative v over 2. And then, to avoid rewriting these constants in here, we can designate it as just constant c. So we have here equal to c times e raised to negative u squared over 2 times v raised to n minus 1 over 2 minus 1, then e raised to negative v over 2, which is this joint PDF for u and v. Now let us do the transformation from this PDF in here into this PDF in here. So joint PDF in terms of T and W is equal to this joint PDF in here, but we need the expression of U in terms of T and W, which we designate as function h1 of T and W, and then expression of V in terms of T and W, which we designate as function h2 of T and W, and then Jacobian of these functions in here. So from above, we can use this. So from that, T is U times n minus 1 over V raised to 1/2. Then from here, U will be T, then over this, or we just multiply it by the reciprocal of this. So we have here V over n minus 1 raised to 1/2. And then we have a simple expression, W equal to V. So we can have here for W equal to V. And then from here, V will be equal to W. And then since V is equal to W in here, it is equal to T times W over n minus 1 raised to 1/2. Then for the Jacobian, it is equal to the determinants of this expression in here is U in terms of T and W, which is this function h1 of T and W. Now for this is V in terms of W, so we can use it as this function h2 in terms of T and W. Now please take note that this term in here is for U in terms of T and W, and this term in here is for V in terms of T and W. Even though there's no T in here, as long as there's no U and V in here, it is enough already as V in terms of T and W. So we can use it as this function in here. So we have here absolute value of the partial derivative of h1 with respect to T, partial derivative of h1 with respect to W, and then we have here partial derivative of h2 with respect to T, and then partial derivative of h2 with respect to W. As a determinant, then its value is the product of these two terms in here, partial derivative of h1 with respect to T times partial derivative of h2 with respect to W, and then minus the product of these two, partial derivative of h1 with respect to W times partial derivative of h2 with respect to T. And then partial derivative of h1 with respect to T is partial derivative of this one with respect to T, which is W over n minus 1 raised to 1/2. Then for this, partial derivative of h2, which is this, with respect to W is just 1. Then partial derivative of h1, which is this one, with respect to W is, so we have here the constant T over n minus 1 raised to 1/2. And then derivative of W raised to 1/2 with respect to W is 1/2 times W raised to 1/2 minus 1 is negative 1/2. And then partial derivative of h2, which is this, with respect to T is 0. Since we don't have T in here and this W is a constant, then this whole term in here will become 0. So what is left is this. So we have here W over n minus 1 raised to 1/2. So now for our joint PDF in terms of T and W, it is equal to this, which is this, but using this and this for u and v respectively. So for this term in here, c times e raised to negative u squared over 2. For u squared, we have the square of this, which is t squared times w over n minus 1. And then we have over 2. So we have in here times 1/2. And then we have this, but we need to substitute this w for v in here. So we have w raised to n minus 1 over 2 minus 1 times e raised to negative w over 2. And then we have here absolute value of the Jacobian. So we have the Jacobian in here. We can distribute this 1/2 for each term in here. So we have here w raised to 1/2 and then over n minus 1 raised to 1/2. And then from here, we can then collect constants. So we have here the constant c and the constant in here. So we have here c over n minus 1 raised to 1/2. And then we can combine this term in here and then this term in here. So we have here w raised to, for its exponent, it is equal to, we have here w raised to n minus 1 over 2 for this one, then minus 2 over 2. And then we have here plus 1/2. So we have here equal to, we have a common denominator 2. So we have here n minus 1 minus 2 is n minus 3 plus 1 is n minus 2. And then we can distribute this over 2 for each term in here. So we have here w raised to n over 2 minus 1. So we have here n over 2 minus 1. And then combining this term in here and this term in here, we have here e raised to, we can have a common factor w over 2. We have here also w over 2. And then we have here negative and negative. So we can have here negative w over 2. And then what remains are this t squared over n minus 1. And then we have here plus 1. So that's the PDF for this t and w. Now for the step 3, we can now derive the PDF for t distribution by integrating the joint PDF. So we have here PDF for t distribution is equal to integral of this with w. Let us move this constant outside of the integral. So we have here c over n minus 1 raised to 1/2 and then integral of. Now for this term in here, to avoid rewriting it many times, let us designate it by b. So we have here w raised to n over 2 minus 1 and then e raised to negative. We have b over 2 w and then dw. Now for the limits of this integral, this w is from v, and this v has a chi-squared distribution, and for a chi-squared distribution, the range of values for its random variable is from 0 to infinity. So we have here, so this should be 0 to infinity. Now to evaluate this integral expression in here, let us use the gamma function. This is defined to be equal to, let us use the variable y instead of t to avoid being confused in t in here. So we have here y raised to alpha minus 1, e raised to negative y, dy. This is from 0 to infinity. Now to evaluate this to be in terms of gamma function, we need to make this to be similar to this. So for this term, let us make this y to be equal to b over 2w. So we have here, let y be equal to b over 2 times w. And then from here, dy will be the derivative of this term. So we have here b over 2 dw. And then for y raised to alpha minus 1, we have here y raised to alpha minus 1. It will become this term in here, w raised to alpha minus 1. Then it will just be equal to this b over 2 raised to alpha minus 1, and then w raised to alpha minus 1. Now let us make this w raised to alpha minus 1 to be similar to this term in here. We can do it by letting this alpha equal to n over 2. So we have here, let alpha be equal to n over 2. Then for this, we have now gamma of alpha, which is now n over 2, equal to the integral of, for y raised to alpha minus 1, we have this b over 2, then raised to alpha minus 1, which is n over 2 minus 1. So we have here n over 2 minus 1. And then for this, we have w raised to also n over 2 minus 1. And then for this, we have e raised to negative y, which is b over 2 times w. And then for dy, we have this. So we have b over 2 times dw. And then for the limits of the integral, from here we can have w in terms of y. So we have here the reciprocal of this b over 2, which is 2 over b, and then times y. Now in here, when y is 0, in here w is 0 as long as this b is not equal to 0. So we have here 0. And then when y is positive infinity, in here, y is positive infinity as long as this b is non-negative, or b should be greater than or equal to 0. Or we can combine both. We can have b to be greater than 0. So if we have a condition with this one, we can put here positive infinity for w when y is positive infinity. Now how to make this b to be greater than 0? In here, to make this b to be greater than 0, and also avoiding this b to be approaching infinity, we need to make this n minus 1 to be not equal to 0. Or from here, n should be not equal to 1. But this n in here is the number of samples for the sample random variable in here. Then this n should be at least 1, or we say greater than or equal to 1. So in here, from above, n should be greater than or equal to 1, and then combining both of these, we need to make this n to be at least 2, so that it will not become equal to 1. Then, satisfying this condition, this n minus 1 will become greater than 0. Since this t squared is always positive, no matter what the values of this t in here, then this whole term will become greater than 0 as long as we satisfy this condition in here. So we need to put a condition in here, n should be greater than or equal to 2. And then, in here, we can combine both constants, this and this, so it will become b over 2 raised to n over 2 minus 1 plus 1 is n over 2. Then we can put it outside of this integral. And then what remains in this expression here, it is saved with this. So now this expression in here will be this gamma of n over 2 over this constant. So we can put it gamma of n over 2 and then over this, or we can just multiply it by the reciprocal of this. So we have here 2 over b raised to n over 2. So now let us use another sheet. So now our PDF in terms of t will be equal to, we have here c over n minus 1 raised to 1/2 and then times this. So we have here gamma of n over 2 and then we have 2 over b raised to n over 2. And then let us now bring back the constants c and b. So we have here, for c we have this for c, so we can put it there. So we have 1 over square root of 2 pi, then times 1 over gamma of n minus 1 over 2, and then 2 raised to n minus 1 over 2. This is for z. And then we have here 1 over n minus 1 raised to 1/2 for this, and then we have gamma of n over 2, and then we can distribute this n over 2 for 2 and b, so we have here 2 raised to n over 2. Then for b raised to n over 2, we need to bring back the b, so we have this b t squared over n minus 1 plus 1, t squared over n minus 1 plus 1 raised to n over 2. And then we can combine this 2 in here, this 2 in here, and this 2 in here. So we have here 2 raised to, since this 2 is at the denominator, so we have here negative 1/2, and also this 2 in here is at the denominator, so we have here minus n minus 1 over 2, or we can just distribute this over 2 for each term in here, so we have here negative of n over 2, and then we have here minus negative of 1 over 2, which is plus 1/2. And then we have here at the numerator, so we have here plus n over 2. And then we can have 2 raised to, we have here negative 1/2 and plus 1/2, and then we have here negative n over 2 and plus n over 2. So it results in 0 or equal to just 1. So we can just cancel this 2 in here, this 2 in here, and this 2 in here because they result in 1. Let us collect this gamma function and this gamma function in here, so we have here gamma of n over 2 and then over gamma of n minus 1 over 2, and then we have here 1 over, this is square root of n minus 1, and then combining it with this square root of pi, we have square root of pi times n minus 1, and then this, we have 1 over t squared over n minus 1 plus 1 raised to n over 2. So this is the PDF for t distribution, and we have a parameter here n, which is the number of samples, so we have here n, and then for its degrees of freedom it is n minus 1, so we can put here with n minus 1 degrees of freedom. Now we also need to put our condition, this n to be greater than or equal to 2. So we need to put here n should be greater than or equal to 2. Now we can express this PDF for t distribution to be in terms of the number of degrees of freedom as its parameter rather than its number of samples, so we can put here let p to be equal to n minus 1, which is its degrees of freedom. So our PDF for t distribution in terms of the parameter p will be equal to, from here we have n is equal to p plus 1, so in here we have gamma of n, which is p plus 1 over 2, and then over gamma of, we have here n minus 1, so we have here p over 2, and then in here we have 1 over square root of pi times n minus 1, which is p, and then in here we have 1 over, so we have p squared over n minus 1 is p, and then plus 1, and then raised to n over 2, we have here p plus 1, and then over 2. So we have here this condition, p plus 1 should be greater than or equal to 2, or p should be greater than or equal to 1. So we have here with p degrees of freedom, with limitation that p should be greater than or equal to 1. So we have now our PDF for t-distribution in terms of parameter p, which is its number of degrees of freedom. So now let us proceed with the appendix of this video, which is proving that this expression in here, which is designated as random variable u, has a standard normal distribution. Now in this expression, this x bar in here, which is the sample mean, has this formula in here. This x sub i's in here are the sample random variables. There are n of them, so this n is the sample size or the number of samples. This sample random variable should be IID, so they should be independent to each other and they should have identical distribution, which is a normal distribution. So they should have the same population mean mu and the same population variance sigma squared. So this mu in here is same with this mu in here. The sigma in here is same with the sigma in here. So to prove this, we need to use the theorem that random variables which have the same moment generating functions have the same distribution. So what we need to do in here is to prove that the moment generating function for this u, which is this, is the same with the moment generating function for random variables which have this distribution. So now let us determine the moment generating function for u. So we have the formula for the moment generating function. It is the expectation of e raised to, we have here u times t, and then substituting this for u, we have expectation of e raised to, this term in here, we can put here x bar minus mu over sigma over square root of n, and then we have here times t, so we have here t in here, and then from algebra we know that e raised to a plus b is equal to e raised to a times e raised to b. Then distributing this t over sigma over square root of n for each term in here, and then applying this, we have expectation of e raised to x bar times t. Now for the square root of n, so we have here over square root of n, we can put it at the numerator, so we have here square root of n, and then we left with sigma for the denominator, so we have here sigma, and then we have here e raised to negative mu, then times t, and then times square root of n, and then over sigma. Now this mu, t, and sigma are constant, so this whole term will be constant, and then we can put it outside of this expectation in here. Then we have here now e raised to negative mu t times square root of n over sigma, and then expectation of e raised to x bar times t times square root of n over sigma. Now let us evaluate this. So we have here expectation of e raised to x bar times t times square root of n over sigma, and then using this formula for the x bar, we have expectation of e raised to, for x bar, we have x sub 1 plus x sub 2 plus x sub 3 plus etc. until x sub n. Then we have here over n, and then being multiplied by t times square root of n over sigma. Now in here we have n over square root of n. We can have n raised to 1/2 minus 1 is n raised to negative 1/2. So we can just cancel it, and this n will become square root of n. So we have here now the constant in here. Combining all this constant, it will just become t over square root of n times sigma. Now for this term in here, let us designate it with the constant r to avoid rewriting it many times. So distributing this r for each term in here and then applying this, we have here expectation of e raised to x sub 1 r times e raised to x sub 2 r times e raised to x sub 3 r times etc. until e raised to x sub n r. And then, now if we have two random variables, let's say, let us use the random variable y and q, and if they are independent to each other, then expectation of their product y times q is equal to the product of their expectations. So we have here expectation y and expectation of q. Then in here, this x sub 1, x sub 2, x sub 3 until x sub n are IAD, therefore they are independent to each other, then their function should be independent to each other. So this e raised to x sub 1 r, this e raised to x sub 2 r, this e raised to x sub 3 r, etc. until e raised to x sub n r should be independent to each other. Then treating these terms in here as random variables and then applying this for more than two random variables, then we can distribute this expectation in here for each term in here, like what was done in here. So we have here expectation of e raised to x sub 1 r times expectation of e raised to x sub 2 r times expectation of e raised to x sub 3 r times etc. until expectation of e raised to x sub n r. And then for this term in here, this is a formula for a moment generating function similar to this, but instead of t, we need to use the constant r, which has this value in here, and instead of u, we need to use the random variable x sub 1. So this term in here is the moment generating function for x sub 1, and then we need to use the constant r. Now for x1, it has a normal distribution with population mean mu and population variance sigma squared. So in here, you can find in several references that the moment generating function for a random variable which has a normal distribution with population mean mu and population variance sigma squared is e raised to mu times the constant in here, which is r, and then plus the population variance sigma squared times this r squared, and then over 2. So now let us bring back this constant for r in here. So we have here, this is equal to e raised to mu times this t over square root of n times sigma, and then plus, we have here sigma squared, and then square of this, we have t squared over n times sigma squared, and then 1/2. And then we can cancel out this sigma squared and sigma squared. So we're left with this. And then for this term in here, it is similar to this. So it will be moment generating function for x sub 2 using the constant r. But x sub 2 is same with x sub 1. They have the normal distribution, so they will still use this formula in here because they have the same distribution. So the value of this one will just be this. And then also for this term in here, it will just be this, and then etc. until this. It will have a formula same with this. So what happens now for this expression in here, it is equal to this expression being multiplied n times. So we have here expectation of e raised to x bar times t square root of n over sigma is equal to this term e raised to mu t over square root of n times sigma, and then plus t squared over 2n, and then b multiplied n times. And we know from algebra that e raised to a raised to b is equal to e raised to a times b. So we can just put this n inside in here. So we can just cancel it and put it inside. So we have here mu t times n, and then putting it in here n, and then we can just cancel it with the n in the denominator. And in here, n over square root of n is n raised to 1 minus 1 half is n raised to 1 half. So we can just put it square root of n, and then we can cancel out this square root of n in here. So what we're left with in here is e raised to mu t times square root of n, and then over sigma. And then in here we have plus t squared over 2. And now we can use this expression in here for this in here. So let us copy this. So we have here our moment generating function for u is equal to this term. So we can just replace this by this expression in here. So we have and then applying this below from here to this form in here, we have in here it will become e raised to, we need to add this and this term in here is same with this term in here, and this is negative and this is plus, so they will just cancel each other, and then we're left with t squared over 2. So we have here t squared over 2. Now for a random variable which has a standard normal distribution, its moment generating function is e raised to t squared over 2. You can find it in several references. Comparing this to this, they are the same. So the moment generating function for u is the same with the moment generating function for z. Thus they have the same distribution. So this u has a distribution same with this, which is a standard normal distribution. So we have here a standard normal distribution. So now we have proven that this u has a standard normal distribution. So we have now proved this. So this ends this video, and I hope you learned a lot from this video, and to the next video as well. So thank you for watching, and don't forget to subscribe in my channel.